Hello and welcome. Today we're diving into the single most important idea in mathematics, and that is the function. Before we even look at a single graph or equation, let me ask you some questions to prime your brain. So first, can a single student ever have two completely different official student ID numbers at the same time? Second is, if I tell you the date right now, can you tell me exactly which day of the week it is every single time? And for my last question, if you are using a vending machine, can you press A4 and sometimes get a chocolate bar and other times get a bag of chips? The consistent answers to those questions, the yes or no that never changes, are the reason functions exist. They represent reliable, predictable relationships in mathematics, science, and life. The goal of this entire instructional video lesson is to give you the ultimate tool to definitively state when a relationship is one of those reliable functions and when it's just a messy general relation. Now let's move to what is relations and why it is connected to set theory. The entire discussion in this video lesson starts with sets. And a relation is the most basic concept rather because it simply means that any connection you define between two sets of numbers or objects. Now let me introduce to you the anatomy of a relation. This is very important, especially when you learn about functions because we use specific language to describe these sets and you learners must master this anatomies. First is the domain. This is the starting set. We often think of this as the set of inputs, and when we say inputs, that is the x values, right? And another one we have here, the codomain. This is the ending set, or this is the set that contains all the possible outcomes, possible outputs, and that is mostly known as the set of y. And for the range, this is the subset of the codomain that contains only the outputs that were actually connected to an input. Every single set of ordered pairs you've ever worked with is, by definition, it is a relation, but only a special, discipline type of relation gets promoted to a function. Because remember this unbreakable rule. Yes, there is a rule that is unbreakable in function, and the rule that separates a function from a general relation is absolute. It says that every input must have exactly one output. What does it mean? If an input in the domain ever connects to two or more different outputs, that connection is instantly broken and the entire relationship is demoted. It remains only a general relation. It is not a function. So we'll run through the three progressive tests required to truly master this distinction, moving from abstract set theory to visual proof. What is the many-to-one truth and what is the one-to-many failure? Okay, let me discuss each topic. The many-to-one truth is, look at our first scenario. If T goes to 4 and O also goes to 4, that is a many-to-one map. This is a function. It's fine for two different inputs to share the same output, and the rule only governs the outgoing arrows from the domain. While the one-to-many failure is that when we combine relations using the set operation union, we created a new pair where the input T maps to both 4 and 5. This is a critical failure because a one-to-many map shows one input splitting its mapping into multiple outputs, and that is illegal. That is illegal, and it's the clearest visual sign that the relationship is only a general relation. A function is distinguished from a general mathematical relation by a crucial constraint concerning its inputs and outputs, which are derived from sets, and specifically a relation is any defined connection between the elements of two sets, the domain, or again the domain, that is the input set, and the range, that is the output set. For a relation to qualify as a function, every single member of the domain must be mapped to exactly one number of the range. This requirement strictly prohibits one-to-many relations where a single input value could yield multiple different output values. So let me give you an example. For example, the linear equation y is equal to 2x, that is a function. Why? Because any single x value yields only one corresponding y value. And conversely, the equation y squared is equal to x, that is a general relation, but not a function, because an input like x is equal to 4 results in the two distinct outputs, y is equal to 2 and y is equal to negative 2. That violates the rule when you are distinguishing function from a general relation. This fundamental constraint is the key to identifying a function, which can be visually confirmed on a graph using the vertical line test, which I'll be discussing later on, because if a vertical line intersects the graph at more than one point, the single input corresponds to multiple outputs. Thereby, it disqualifies the relation as a function. So now, I want you to analyze this given Venn diagrams. Okay, I want you to analyze that. I want you to determine if that is a function or a relation and why it is a function and why it is a relation. Now, we must ensure the rule holds regardless of the data that is presented, because we have here the application across representations, and let me introduce to you the representations of functions. First representation is the table or the ordered pair. So if you are checking a list of ordered pairs, you only need to look for repeated x values, and if you find that the x values are repeated, it is not a function already. Here's an example. Okay, so this image illustrates the key distinction between a function and a general relation that is not a function when represented in a table of values. Because again, the fundamental rule for a function is that every input must map to exactly one output. And in the table on the left, it was labeled function. We observe that inputs negative 1, 0, 1, 2, and 3, that is a function. Importantly, although you can observe that the output value 4 repeats, right? This is perfectly acceptable in function as it is a many-to-one relationship. That is, different inputs can lead to the same output, but crucially, no single input is paired with more than one output. And by contrast, the table on the right, labeled as a not function, it clearly violates this rule, right? So, if we examine the input set 3, 4, 5, and 10, we see that the input value 4 is repeated, and the first instance of 4 yields to an output of 7, and the second instance of 4 yields to different outputs of 14. Right? So this shows a one-to-many relationship where a single input 4 is associated with two different outputs, that is 7 and 14. Right? So because a function cannot have one input leading to multiple outputs, the relation shown in the right table is disqualified from being a function as it fails the essential test for uniqueness of the output value. So that is not a function, that is a relation, and the other one is a function. The second representation is the VLT, or let's have the graphical check. For graphs, the vertical line test VLT is your tool. A vertical line represents a single x input. If that line touches the graph at more than one point, it proves one point has two outputs. And the VLT, or the vertical line test, is merely the visual confirmation of the failure of the one-to-many map. Okay, so I want you to observe this graph. Here's an example. The provided graph is not a function. Why? Because this graph follows the vertical line test, which is the definitive visual test for determining if a graph represents a function. And the vertical line test states that if a vertical line can be drawn anywhere on the graph and it intersects the curve at more than one point, then the relationship is not then the relation is not a function. So in this graph, which appears to be a parabola opening to the right, such as x is equal to y squared minus 1. If you draw a vertical line anywhere to the right of x is equal to negative 1, for example, x is equal to 1, that line will intersect the curve at two distinct points, one above the x-axis and one below it, right? As you can observe in the graph, that indicates that a single input value is paired with two different output values, right? It violates the strict function rule that every input must map to exactly one output. So, this vertical line test is also very important when you are distinguishing function from a general relation. Okay, so now let's move to this ultimate test when you create the different types of mappings yourself and explain the rules of the arrows. First is the legal arrow movement. When you created the function, you made sure that arrows from the domain could arrive together at an element in the codomain or the many-to-one rule, because this is the movement we allow. We only allow in function. The next is the illegal arrow movement. When you created the relation, you made an arrow leave an input and split. This splitting arrow is the single absolute violation of the function rule. So your mastery is achieved when you can look at any diagram and instantly state that the arrow is leaving and it's splitting. It's not a function, it's a relation. So why did we spend all this time dissecting the difference of a relation and a function? Because in a world full of messy and predictable relations, functions represent predictability. Remember that. When you write y is equal to 2x plus 15, plus 1, you know with absolute certainty that for x is equal to 5, you will always be getting y, which is 11. It will never be 12, right? That consistency is what allows engineers to build bridges, software developers to write code, and scientists to model the future. So you now have the power to define that predictability, and you can identify that single point, the single input that causes a system to collapse into chaos. So we've done it. You know how that that a function is a relationship with a very strict rule: one input, one output. You know how to find the rule breaker, right? And that is the repeated input in any format. So go forth, use your set definitions and mapping diagrams, and find the truth in the relationships you encounter. Thank you.